does that limit exist? As you go to 0, 0, 0, you still get 0 over 0, right? But you're so darn close, man. You're so close.
0.
No.
Would be 0.
You told me to remove what?
The sine squared y.
Okay, I claim that I want the opposite of exactly what you're saying. Why don't we just use sine squared y? Now, why? Tell me about this. Tell me about that number.
The denominator is always greater than
The denominator is always bigger than the numerator. Always, right? Unless y is 0. If y is 0, it's what? 1, and then it's sine squared y. Any other case, this denominator is bigger than the numerator. And if the denominator is bigger than the numerator, that fraction is smaller than 1, which means that I'm multiplying sine squared y by a number that's smaller than 1, which means that this would have to be smaller than 1 times sine squared y. Do y'all see that? I wouldn't want x squared here. Oh. Oh, you could have put x squared here. Well, every day about this time, right? I'm not quite sure that we could do x squared here. Because, well, is x squared always smaller than this? I don't see, I'm tempted to, but I'm skeptical.
Well, because we already said the bottom's bigger, right? It couldn't be because then this is always less than 1, and x squared is quite big.
The problem is the sine squared y. Is that part going to mess up? Is there an x I could plug in over here and a y that I could plug in over here that would make this term smaller than this term? I'm not sure. I'm just not ready to go out. I know for sure I can say this because I know this ratio is always less than or equal to 1. So this expression is always less than or equal than this expression. Maybe we'll come back to it. Yeah. I mean, maybe x squared works here, but I'd have to convince myself of that. I know 0 works, right? 0 is definitely less than that. But the beauty of using sine squared y is where does that go when you take its limit? We're letting x and y go to 0, right? And then that goes to 0. So when I take the limits on these, limit as xy goes to 0, 0, then this thing goes to 0. And of course, this side was already going, already 0. So that means that this right here, when we take its limit, must also go to the same place. So this limit is 0 without checking a single path. But you have to be able to squeeze. If you can't squeeze it, then you can't do it. Does this make sense or not? I'm curious. Is x squared, this is a question, is it always less than x squared sine squared y over x squared plus 2y squared? It just doesn't seem like it is. I could do a cross multiply. I can multiply both sides by this. I don't have to worry about flipping the inequality over because this is always a positive number. So we only flip inequalities when we multiply by negatives. So I'm going to multiply both sides by that. I get x to the 4th plus 2x squared y squared. Is that less than x squared sine squared y? Is that always true?
You can take an x squared on both sides?
No, it's not. Let's let x be 1. Okay? Let's let x be 1. I don't think this is going to work. If x is 1, then this would be 1 plus 2y squared, right? Less than or equal to what? Sine squared y. No. Because what if y is 1? Then this side's 3, right? 3 is not less than sine of anything, right? Sine is bounded between -1 and 1, so this wouldn't work. Do y'all see what I'm saying? I think I found an example of why this wouldn't work. And then you try algebraically to convince yourself it's always true. Now, this right here, picking this, was just because now that you've seen this, right, you're like, okay, this trig function's bounded. Like 0 to 1 is the most I'm going to get on this. So I put it here. As long as you can show that this right here is less than 1, use it, because trig functions are easy to take limits of. So in hindsight now, you kind of see where you want to go after that. I feel like I messed up something here. Does this seem right to y'all? Because y'all are looking at me like I'm crazy.
It seems right.
It seems right, right? Just multiply.
Sure.
Yes? Uh-huh.
Could you also do like a numerical approach where like you pick a negative number that's really close to 0 but not at 0, and then a positive number that's really close to 0 but not 0, and then plug in both, and if they're the opposite, you know, it doesn't exist. And then
Like numerically test some different small numbers near 0?
yeah.
And then see what it heads towards. That would be in the realm of like the epsilon ball type idea, is that you're getting points closer. But the thing is, you still have to check. I mean, that could be very dangerous, because think about this. You remember on that problem that we did where we checked every single line
Yeah.
and all of them gave us the same answer?
Yes, sir.
The only one that worked, that gave us something different, is when we came in along the parabola like that. So let's say you pick a point, right? Let's say you pick all these points that are here, and you just do a bunch of them that are really close to them, 0, 0. And you get the same answer every time. The only way that you would have got a different answer is if you would have picked a point off that parabola. And that would have been dangerous, right? Because what are the odds you're going to pick one off that parabola? You know what I'm saying?
Oh.
You would have to pick like x would have to be your y coordinate squared. So like whatever you pick for your y, your x would have to have been exactly that number squared, and then you would have got a different answer. Is that making sense?
Yeah.
Yeah, so yeah, a guess and check would be pretty dangerous in a situation like this. So it's either going to come down in your homework to one of two things. You're either going to be showing that something, the instructions are going to say, show it does not exist. And in that case, you know that it's just some paths. You've got to find the paths that don't work, that don't match up. The other thing is it'll say, show it exists, or find the limit. And when it says that, that means you have to do squeeze. I'm pretty sure that's it for this section. Oh, no, sorry, continuity. Well, continuity is an even stronger condition than a limit existing. So back again in Cal 1, when we graph a function like this is Cal 1, does the limit exist at A here? Does the limit exist?
Yes.
Yes, because it's approaching the same thing from the left and the right. So in Cal 1, the limit exists. Is this function continuous at A? No, because there's a hole. So the only thing to do continuity, we need it to be like filled in here, right? That way we can draw without picking up our pencil. So if we're going to talk about continuity here, the first condition is that the limit exists. And then that we have a filled in hole there, that it's filled in. We already know how difficult it is to show that the limit exists. So showing that something is continuous is also very difficult to do. But it's okay. We have a nice little result. And it says that we don't have to worry too much about it, that someone else has already proven this for us. Mathematicians have suffered, and they have proven that all of these functions are continuous on their implied domains. So all polynomial functions, f of x, y, are continuous on the entire plane. So if someone gives you a function, f of x, y is equal to like x squared y plus y to the fourth x minus 4x y to the fifth, that would be considered a polynomial function of two variables. Just a bunch of powers of x, right? Looks like a polynomial. This is continuous everywhere, which means that every point you pick on this surface, as you approach it from any path, it goes to there's a limit and it goes to the point it's approaching. So there's no jumps, no breaks, no holes, nothing. Everything's great. And that works for all polynomials, all rational functions, as long as you're on their implied domains. So as long as you're talking about where they're defined, they behave well. And then the composition of continuous functions are also continuous. So if you take a continuous function and plug it into another continuous function, you still remain continuous. This is not super important, all right? I'm just showing you that we can still proceed in this class, even though we can't do limits very well, and it's difficult, we can still proceed because we have these results. Yes?
So, question about these.
Yeah.
These are all for, none of these are for 3D, right?
These are all surfaces. Remember, all these functions of two variables are surfaces in three-dimensional space.
Oh, okay.
So it's like, imagine these are all like blankets, okay, like floating in the wind. Freeze it, right? Take a picture, freeze it, and you got this blanket. As we walk along this blanket, it's nice and continuous. We're not going to fall into any pit, like bottomless pits. There's no holes. As long as we're in the domain of the function, we're good to go. But you have to be a polynomial or rational function, or a composition of two. Yeah, okay, so I did think we were done. All right, well, I'd love to give you the rest of the day off, but... Pardon? I'm looking. I don't think we're behind. I think we are kind of caught up. Let me see here. Let me restate that. We're always going to be behind. Like, even this schedule is behind no matter what. Like, there's not enough time later to do things. So every path you try is going to fail, yes. Let's see here. Today is the 13th. Limits, functions, yeah, okay. We're good. Now the take-home that's due on the 18th, right? That's on Monday. No, Monday. What can I see it? Who has it? Right there. Yeah. I just wanted to see, I think it covers up just through chapter 10, right? Yeah. Yeah, so everything on here we've done. Like, we're ready into chapter 11, so everything on here you should be able to handle. In theory, okay?
Does it cover some of the stuff in the previous take-home test?
Does which one?
Does this take-home test cover some of the
I don't recall, actually. I don't remember if there's any topics on the second one that were on the first. How are y'all feeling? All right, you all right? Okay, so in Cal 1, what happened next? In Cal 1, you do limits, and you do continuity, and then you do derivatives. So that's what's next. Partial derivatives, though. So I guess we're not going to go like full-fledged derivatives. We're only going to do partial. What are they talking about, partial derivatives?
When you
All
have
right.
two different variables.
Yeah, you have two different variables, and that's going to have an impact. So we're going to remind ourselves in Cal 1 what the derivative meant. Right? The derivative was just the slope of the tangent line, right? That's all it was. So if I move around on this function, there is only one tangent line, right? There's only one. I only have one choice for the tangent line. The derivative was the slope of it, right? Which was the pitch of the line. The problem we encounter with functions of several variables, well, is that we have two variables. This makes determining a single tangent line very difficult. So let's see how this goes. Okay. All right, here's a surface. Okay, we all see this? We have a point. Try and move this point where we can see a little better. Come here. Where are you going? Get back over here. There we go. Okay, everyone see that point on the surface? Now, what is the slope of the tangent line? Well, in Cal 1, there was just like a curve, and it made sense. There was only one line, right? So what am I talking about here? Slope of what tangent line? So I like to think about it this way. Let's say that's you standing up on that surface, right? Well, you know what? Let me go back and refer to this. Let's say that's you standing on top of there, right? Like a balance, like balancing on tightrope walker, right? But except it's a weird tightrope, right? You're like that. So if I'm right here, my next step is either that way or that way, right? I'm either going to step this direction or I'm going to step this direction. If I step that direction, then I'm going to be stepping up because the slope is positive, right? So I'm going to be increasing. And if I step backwards, I'm going to be going down. But I only have that way or this way to go, right? If we go to the surface, and now I'm standing on top of that surface, and I go to take a step, what direction can I point in? Yeah, any direction I want, right? So when I talk about slope of a tangent line, the direction matters. If I point this way, it might be like, whoa, I'm going down. Whereas if I point this way, it might be like a step up. It all depends on the direction, right? So to start everything off, what we do is we just look at two directions. Right? We're just going to look at the two that make the most sense. So one of them would be, remember the room is the x-axis, y-axis, z-axis, right? The directions that would make most sense would be me facing parallel to the x-axis, right? That would be a sensible first starting point, or me facing parallel to the y-axis. Does that make sense? Those would be the most sensible places to start. So let's start if we point out the x-axis. If I point out the x-axis, then imagine now, so here's my x-axis, here's my y-axis. So that was me standing on the surface over here, right? So if I'm just pointing down the x-axis, then I'm fixing myself onto looking just down that plane. You'll see that? So now I'm just looking this way. And now when I take a step, right, if I'm forced to be on that plane, then there is only one way for me to go. Here's us looking at it from the side. See, if we look at it from the side, we're back in Cal 1, aren't we? So long as I'm just allowed to go in that direction or that direction, parallel to the x-axis, or to the x is actually the xz plane, then there is only one derivative answer, right? It would be the slope of that tangent line, just like in a Cal 1. Now, what if instead of me doing that, instead of me looking that way and walking this way, what if I look that way and walk this way? Then it's going to be cutting it that way instead, right? And then walking along there. And again, if we look from the side and take the surface out, we're just back to another Cal 1 problem, right? This is what the partial derivative is. Partial derivative meaning that you're not really doing, there is no like true derivative of a surface. It's all dependent on which way you face. And so we are partially taking a derivative. Does that make sense? Let me bring this back in. Let's go back to our normal view. Let's go back to this one. When we face, let's go down to back to the first one. When I face down, and here's the x-axis and the z-axis, if I'm facing this way and I'm going to walk, right? As I walk, does my y-coordinate ever change? My y never changes, does it? As I'm walking, going up and down, y-coordinate's fixed. So when I fix y to be a constant, see in my code here I put fix the y value. When I fix the y value, that means y is going to be maybe 1, or maybe y is 2, or y is 3. But y equals a constant is a plane, right? And that's why this green thing is your y equals a constant. Now I made this code so I can move it. So if we're somewhere else on the surface, right? Now if I move my y over, now if I start walking, you know, so it's like I was doing this, but what if I move this way? Start walking again this way. So, but you have to hold the y constant as you move in order to do this. Now if you want to slice it the other way, now you have to hold what constant? The x constant. Go back. Let's hold y constant again. Let me slide this guy back up here. Now, I'm actually going to show you the slope. So now as I walk across, remember I'm holding y constant and I'm moving x. See, there's my tangent line. I have a tangent line as I walk. And it's changing, right? But it depends on x, doesn't it? It depends on the x coordinate. Y coordinate doesn't matter. Y is fixed. Oh, wow, check this out. What if I slice it this way and I show that derivative in the other direction too? And let's take all those planes out of there because they're confusing. Then that would be like a derivative in this direction along with the derivative in this direction at the same time, right? And what if I somehow combine those two? It's almost like I have a direction, right? This way and a direction this way, almost like two vectors. And that those two like vector-looking things, they define a plane, don't they? And that we later on will be able to find what we call the tangent plane to the surface. So as we walk across it, we'll have this like idea of a plane moving along the surface. But that's coming. All right. Visually, do you understand what we're trying to do? Okay. Now, mechanically, here's what we do. If we're given a function of two variables, z equals f of x, y, if we hold y constant, then we call the derivative the partial derivative with respect to x. If you hold y constant, it's the partial derivative with respect to x. So whatever you're with respect to is the part that's the variable. The other variable is held constant. And here's how we denote it. F subscript x of xy. So you know back in Cal 1, this was enough for us to say, hey, take the derivative, right? That was enough. We can't use that notation because we have more than one variable. So I have to be very specific now about which variable is staying a variable and which variable is being held constant. So by writing a subscript x here, this is the way I'm telling you that x is the variable and the y is the constant. Right? So that's the new notation for a derivative now. This means a derivative. It's f subscript like that. Now there's some other notations we're going to use too, but that's your introduction. Now, the other way is that if we hold x to be constant, then we will call it the partial derivative with respect to y, and all we do is replace that x with a y down there. That's it. Here we go. First example. Has anybody here ever done partial differentiation before? Partial derivatives? Taken partial derivatives? Okay. This is one of those things where it might be a little bit weird in the beginning, but then hopefully you'll start to pick up on it, and then once you get it, I think things start to flow pretty nice. So let's do this first one. Part A. We're trying to find the partial derivative with respect to x at the point 2, 1. So the first thing I'm going to do is I'm going to actually just find what the derivative is. I'm not going to plug any values in. I'm just going to find out what the derivative is. And I'm doing it with respect to x, which means I'm holding what constant? The y is a constant. So look at the original function, please. Look at the original function. And I want you to imagine now, imagine if you will, that every y that you see up there is a constant. So maybe y is 1, okay? Just in your mind, imagine that y is 1. And give me the derivative with respect to x. So if this is 1, then that's 1 cubed. That's a constant. It's 0, right? Derivative of a constant, 0. So I get 0 there. I'm going to put the 0 here even though I don't need it. Plus, now, what's the derivative of 2x if we're differentiating with respect to x? 2. Just 2. Okay, so that's 2. Everything seemed pretty natural? Okay, now next part, plus
2xy to the fifth.
2xy to the 5th. Now, you might be thinking to yourself, product rule. But the thing is, y to the 5th is a constant, right? Y to the 5th is a constant. And constants, when we take derivatives, always just come along for the ride. So I'm just going to ignore the y to the 5th, and I'm going to take the derivative of x squared, which is 2x. And then I'm going to slap the y to the 5th next to it. Do y'all see that? It's not like implicit differentiation. You're imagining that one of your variables is a constant. And I'm done here, right? I'm done. Move on. Derivative 10? 0. And that is it. Does that seem pretty straightforward so far for the first example? Now, I haven't answered the question. What's the partial derivative at 2, 1? So you plug in, 2 for x and 1 for y, right? 6? Yeah? Do y'all understand this? So here's what's happening. If I graph this, if I were to graph this, it would be a surface, right? It would be a surface. If I were to walk out on the x-axis, 2 spaces, walk on the y-axis, 1 space, plug myself into the function, I would go up or down, I'd land on the function, right? I'd be somewhere on a surface. And now, if I pointed myself in the direction like this, parallel to the x-axis like this, and take a step, where am I headed? Up. And pretty steep, right? 6 is a pretty good slope. So it's a pretty good rise that direction. Make sense? What we're going to be looking at later, and one of the big questions is going to be, if I'm standing on a surface, what direction do I need to point into that would give me the steepest ascent? Can we even figure that out? It seems like that might be hard. Or you could also ask the question, if I'm on a surface, how do I go? Where do I point so that when I take a step, I don't go up or down? I stay flat. And if you can do that and walk your way around the surface, you will have what we call contour lines, like elevation lines around a surface. But that all has to do with this derivative idea. We're getting there. All right, part B. How about part B? Now we're taking the partial derivative with respect to y. And so now we're going to treat x like it's a constant. We're going to let y be a variable and go to town. So what's the first part become? 3y squared. 3y squared. All right, plus, that's going to be 0, right? Because x is a constant, 2 times a constant is a constant, so that goes to 0. And then plus 5y to the 4th, x squared. So again, x is a constant, x squared is a constant. Ignore it. Derivative of y to the 5th is 5y to the 4th. But then hit it with the x squared. I'm going to actually write it like this. Doesn't matter. This is multiplication. Doesn't matter what order this goes in. And then anything else? That's it, right? Derivative of 10 is still 0. Okay. Now plug in 2, 1. What do we get there? 3. And then what?
4 times 5.
23?
Yeah, 23.
Is that right? 23? Whenever we get to the arithmetic, my brain just stops. It just says, nope, not doing it. So do you all agree with that? Okay. Wow, so we thought we were over on that surface. We stepped out 2, went over 1. We looked that way and we went, whoa, 6. But if we turn this way and take a step, it's like 23, right? Super steep. Oh, okay. Okay, I see where we're headed now. Oh, so these derivatives are going to get harder then. Yeah, the derivatives are going to get harder. All right, so first we're going to take the partial with respect to x. Partial with respect to x. What means we're going to treat y like a constant, right? Let's see here. All right, please sign in. I hate doing the sign-in stuff. I mean, we're in college. What the hell? I mean, really, right? The state actually requires it. Y is a constant. So what first?
Yeah, you do the cosine of x, so it'd be cosine of all that, and then...
Yeah, so we're doing chain rule, right? We have to do chain rule. So we have to start by taking the derivative of the outer function, which is the derivative of sine of something, which is cosine of it. Cosine of everything, right? Can't do anything about it. And then times now the derivative of what's inside, the derivative of the argument. And that's going to require what? Quotient rule, right? Quotient rule. So let me just jot this down over here because we're going to need to do quotient rule on it. So if I want to take the derivative of this using the quotient rule, I'm going to do the derivative. So everyone's learned the quotient rule different ways. I've heard this high D low, low D high. I've heard of it all. I've seen it all. Okay. I always teach my students it's the derivative of the top times the bottom minus the derivative of the bottom times the top. That's the way I teach it. I trust you can do a quotient rule at this point. All right? So let's do the quotient rule, but let's be careful because y is a constant, right? So what is the derivative of the top?
Y.
Because I want to know, please. I know. So derivative, I know, I'm trying to be funny. It's not working. So derivative of the top is y, right? With respect to x, so, right? Now times the bottom, right? Minus, now the derivative of the bottom with respect to x holding y as a constant. 2x plus 0. So just 2x. So that is the derivative of the top times the bottom minus the derivative of the bottom times the top. Oh, I forgot the top, didn't I? xy. And then all of that over bottom squared. Any questions on the quotient rule with the partial derivative on this? Like why anything is what it is? Now's the time? No? That gets tacked on to the end of that, doesn't it?
Yeah.
And I think I can clean it up, can't I? Like this right here is x squared y. And that's y cubed. And then that's minus 2x squared y. Right?
So that would just be negative x.
Yeah, so we should, I think, have y cubed minus x squared y. I'm seeing some looks on your faces. Do you have a question? Or is that just what happiness looks like? Yeah? And then I'm not asking us to plug in a point here. Okay, so I'm not saying like plug in 2, 1 or anything like that. So now if somebody gives us an actual x and y coordinate, that means tells us where to go walk on the surface, we could tell them, you know, what the slope of the tangent line that direction is going to be. Is that a question? Or
Yes.
did I mess something up? Is that why y'all are looking at me? What? No, ask, come
The
on.
derivative of the top,
Okay, y is a constant.
y is a constant. Yeah.
Okay, so let me help you. What if it was x times 5? Then that would be the same as 5x. And what would the derivative of that be? 5. So since y is a constant, just ignore it. Derivative of x is 1. 1 times y. You still have y there, right?
Oh, so the y doesn't go away.
Y doesn't go away. Derivative of a constant by itself is 0. But if it's attached to a function, right? Derivative of 5x is 5. Derivative of 5 is 0. Derivative of 5x is 5.
Oh, okay.
Right?
All right.
You sure?
Yes, thank you.
Okay. Everyone clear on that? All right. Now, what changes if we do the partial with respect to y? Does this first piece change? It doesn't, right? We still have to do the chain rule. So this is going to be still cosine xy over x squared plus y squared, but then times. This is going to be a little, well, yeah, it's not much different, right?
X and y, right? Like whatever, so it'd be like x cubed minus y squared times x?
Yeah, because this is very symmetric to what we just did, right? When you take the derivative of this with respect to y, you treat x like the constant. So derivative, what is this derivative of this with respect to, sorry, we're doing with respect to y. So hold your x constant. It's just going to be x. So you're going to have this part here becomes instead x and then times the bottom minus derivative of the bottom, which is now 2y, and then times the top xy. And so if you do this again, it's going to, I'll let you work it out, but this will be the same thing, but it'll be x cubed minus y squared x over x squared plus y squared squared. This will be our last note. We'll just end it on this. So you might recall that in Cal 1 again, that there were multiple ways to say the derivative. So like if they said y is equal to some function of x, there's so many different ways to say the derivative. You could say y prime, you could say f prime of x, you could say d dx of f, you could say d f dx. There's so many different ways to say the derivative. And with partial derivatives, it's the same thing. There's a bunch of notations. So this is one notation, partial of f with respect to x of xy. That's the one we started with. But if you just write f with the little x under there, it's understood to be the same thing. Now this is kind of like this one here, but we use a different symbol. We don't use like a lowercase d. It's like a del instead. So it's like a curly d. So there's a big difference between this and the straight d like this. Okay, that's the derivative of f with respect to x, Cal 1. Nothing is being held constant, just the way we've done it in the past. Here, this is telling you, wait, we've got some variables that are being held constant. All right? So we're doing a partial derivative. So derivative of f with respect, the partial of f with respect to x, the partial of z with respect to x, these all mean the same thing. The partial with respect to x of the function of two variables. This one's interesting, f sub 1. That's a 1. It means you're taking the partial of f with respect to the first variable in the ordered pair. So like, you know how this is f of x, y? This is the first variable, isn't it? This is the second variable. So if you write f2, that means you're going to be taking the partial with respect to y. And if this was a function of, let's say, like 10 variables, and you want to take the partial with respect to one of those, you could say like f subscript, whatever, 7 or 8. You could also say capital D, which just means like the derivative. With, again, first variable of the function f. And then this one, again, the derivative, but this time instead of using 1, they just put the damn letter there, x, and put f. Okay, so all these confusing notations. The ones you're going to see the most in this class, here, 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 and here. I'm just kidding. Y'all have a good weekend. I'm just messing with y'all. I'm ready for the weekend. It's only Wednesday. Jeez.